How is that rotational energy different than friction?
Oh, okay. Great. Yeah, great set of questions, and always a question for students when they get to here. Let me start with the first part of yours. When you are having rotation along with translation,
Right.
Your drop in potential energy, let's say you fall a given distance of 3 meters. If all of that energy goes to translation, it goes pretty fast. But if some of that energy has to go to rotation, you give up some energy to translation. So that's why anything in terms of energy, okay, you also asked about friction, but hold on. The first part of it is in terms of energy. In terms of energy, I guess it would be similar to say you have $100 to give away. So you give it to, hey, how about me? All right. So you give me $100 and you know, I'm excited. I got a full $100. However, if you have to use some of your $100 to maybe travel to me, let's say you have to spend $25 to get to me. By the time you get to me, you only have $75 left to give to me. And so I have less money because of that. And that's my silly analogy of something falling. If something falls 3 meters, that's the total amount of energy it has to give to the system. And if you give it all to translation, so if the thing doesn't rotate at all, if it's only given to translation, that's the fastest anything will ever go. So if it's something that has to rotate, like a basketball, you are giving some of the energy to rotational energy. Therefore, there's less for translational, and it will go slow. I'll move on to friction, but it looks like you got some questions in your eyes. Like, wait a minute, I don't think.
No, I'm good. I'm good. Yeah, no.
Okay. So, all right. So with that in mind, we could play the same game about friction. Okay. Now, keep in mind, everything I just said was talking about an object that would roll down a hill. I'm sorry, not roll, move down a hill without any friction. The fastest anything would ever be going, the fastest translating speed anything would ever go is if number one, there was no friction, and number two, there was no rotation, because all of the energy goes to just its translational speed.
Right.
If you have either sliding friction or static friction, it's going to go slower. Okay. Right. And the difference between those is whether it will rotate or translate. Okay. So if something just slides down, you lose some of your energy to friction because there's work being done on friction. There's a force and there's a distance. Now, static friction is kind of interesting. Static friction never takes any energy away. There's never a distance. There's never sliding going on.
Right.
So what static friction actually does is take the energy and turn it into rotational energy. It does not turn it into heat energy. And that's kind of the difference. But let me emphasize again, anytime you have friction, the object will go slower.
Right.
It's just static friction results in the object rotating.
Right.
And that's where the energy goes. Whereas kinetic or dynamic, I'm not sure which term your book uses.
Kinetic.
Okay, so kinetic friction goes into heat when it slides down.
Okay.
So I want to be careful when I say an object at the bottom of the hill goes the fastest when it doesn't rotate. I also meant to say no friction either. No kinetic friction.
Okay. All right. So they're they're not the same, but without the friction, you wouldn't have the rotation.
Right, right. And so the friction is actually what makes the thing rotate. It's that
Right.
it supplies the torque, making it rotate.
Okay, okay. Yeah, I was just trying to figure out how they're related, but they're still two different things.
Yeah. Looking for a good way of saying it, but if you ever have friction, it does, slow it down.
Right.
It just where that energy ends up, because if it slows it down, it loses that energy. Just where does that energy go? And I would say in the static effect, it doesn't show up as heat, it shows up as rotational energy.
Okay.
The kinetic effect, it shows up as heat, it doesn't show up as rotation.
Okay, so yeah, so the heat and the rotation are the result of the friction.
Yeah.
Okay, all right, yeah. Okay. Thank
of
you.
Course, in a real world, you often have a combination of the two.
Sure,
so
sure.
A little bit of heat and a little bit of rotation.
Okay, okay. Well, that helps. I was just thinking about it. Thank you.
All right, good. All righty. All right. Hunter, are you all right? You're the brave one today. Good. I don't know who's gonna jump on here first. I thought it would be Scott. That looks like I don't even see Scott. Did you take off? Okay. All right, but let me do this one next here on our list. All right. So, good. Chapter 38. You guys are moving along. Number 49. And we'll go at 10. 13 here. All right. So, chapter 38, number 49. And let me share my phone here. Okay, that looks good. Feeling a little out of practice. What happens when you miss a week here? All right. Okay. Good. All right. So let me jump over here. Let's see. That's solution. What did I do with the homework? There's homework. Okay. So 37, 38. Okay, here's 38, number 49. Oh, and it says review problem, huh? Okay, well, let's try this here. All right, so 49 says something along this line. A beam of 541 nanometers is incident on a diffraction gradient that has 400 grooves per millimeter. A. Determine the angle of the second order ray. Okay, so maybe just as kind of a quick summary or response of the diffraction gradient. The diffraction gradient has a lot of slits. But the argument is that if you look at the two adjacent ones, of course, then we've got the d sine theta equals m lambda. We just got the double slit type of problem that we did last chapter. And then if you throw a third one in there, well, the third one with the second one are adjacent to each other. So the behavior between the second and the third is a lot like the behavior of the first and the second. So the argument is if you had three slits, if this is the equation that gave you maximums for two slits, it's also the same equation that's going to give you maximums for three slits, and also for four slits and five slits and six slits. So this equation then extends from what we did in chapter 37 with double slit to multiple slits. So anytime you have 2, 3, 4, 5 slits, and we have a lot of slits, they say there's 400 per millimeter. We don't know how big the light beam is. So if the light beam was maybe 2 millimeters, this would be going through 800 little slits. So don't really know how many slits it goes through. But the point is, then it wouldn't matter. This is the location. And so in this problem, then you would have what they would call the first beam, the second beam, the third beam, something like this. And so M would equal to 0 down the middle, M equal 1 for the first time we got constructive interference. And that basically just meant that there was one wavelength further for the between two adjacent, now I'll call it two adjacent slits since we have so many of them. But when we derived it with two slits, we just said that the top slit would travel one wavelength shorter than the bottom one. Anyways, we're looking at the second one here. So we have the question is find the angle, right? Determine the angle of the second order. All right, so we have d sine theta. The M is 2, and the wavelength here is 541, and I'll do it in meters, so I'll call it times 10 to the minus 9 meters. Now, the only added piece to this is maybe figuring out what D is. And so D has the same meaning. It's the distance between slits. Of course, now we have more than 2, so maybe we should call it the distance between adjacent slits. And if we have 400, and I'll just write it as slits or grooves, what do they say? 400 grooves per millimeter. If you take the reciprocal of that, you really have the distance between slit. So I'm going to write that as 10 to the minus 3 meters over 400 and then slit. So this is actually the D. So that might be the tricky part here, is to say, okay, how do I get the D from the information they gave me? So 1 times 10 to the minus 3 divided by 400. So that would be 2.5 times 10 to the minus 6 meters between each slit. All right, so now using that, I could say sine theta, and then there's the 2, there's the 541 times 10 to the minus 9. Now divided by the D, which is 2.5 times 10 to the minus 6 meters, and this is meters, so they're going to cancel off. And I think there's going to be a pretty small angle, so I might not even do an inverse sine. I'll just go the small angle approximation. See what number we get here. 2 times 541 times 10 to the negative 9 divided by 2.5 times 10 to the minus 6. And well, that's probably big enough that I don't know if I should do small angle approximation.
Yeah, I was actually about to say, I forget. What is like the threshold that we want to stay in between if we're making this small angle approximation?
Yeah, see, there's a general rule because it you know, it just slowly gets worse and worse and worse. So I at 0.5, my definition is about 0.5, because 0.5, you're off by about 5%.
Okay, cool, makes sense.
Yeah. So I'm going to go ahead and do inverse sine. And you can see then for the angle, I get 0.4476. And I'm in radians. So you can kind of see that if I just changed right here from a 4.3 to a 4.4. So it was right at my transition point. Okay, so I'll see what the author does here on the solutions. Does he keep it as a small angle and move on to the next part? Or does he do the inverse sine? Let's see. 49. Oh, well, he doesn't have it in radians, but his math shows an inverse sine function. So he does an inverse sine function. And he gets 25.6 degrees. And it makes me wonder if I should switch over to degrees. Let's see. This is radians, so times 180 divided by pi. So this would be 25.6 if we do it in degrees. Okay, so there's a this is good. I see. So maybe this is why it's a review. It says, now what if, so what if the entire apparatus was underwater? What would be the new second order? Okay, so if this is A, here's B, and the, again, reason it's called a review, if you go back to our first chapter, what happened when something was underwater, that index of refraction, well, I guess it lowered the speed, but that's not really relevant for this. It changed the wavelength. And that's what's important for this one. Since D sine theta equals m lambda, and then maybe we should say lambda naught over n here. We're going to have it in some median. So there's the review part. So now this angle would be the inverse sine of, and so it would almost look the same. You would have a 2, and your wavelength in free space would still be the 541 times 10 to the minus 9. And we would still be dividing by D, 2.5 times 10 to the minus 6. But the new thing would be a division by the index of refraction, reducing the wavelength. And if we did small angle approximation, we can just divide that by 1.33. But not doing a small angle approximation, I should, I guess, re-enter this. So this would be 2 times 541 times 10 to the negative 9 divided by 2.5 times 10 to the negative 6. And what's new here is divided by 1.33 for the water. And then if I do, well, even then, so that's even smaller. So makes the small angle approximation even more accurate. But I get an angle of 0.3314. That's radians, and since last time he did degrees, maybe I should check the degrees. So times 180 divided by pi, and so that's about 19.0 degrees. So as we would expect, the angle is different for the different wavelengths, and smaller angle goes with smaller wavelengths. And so that's what the effect of the water did. It gave us a smaller wavelength and hence gave us a smaller angle. So if this was, all underwater back here, or if you had it in a chamber, and then as you flooded it with water, you would see these lines, shrink together. They would narrow in. And it's actually not too much of a surprise, because you would expect that for if you had shined it from the outside and maybe you put the water line right here, they'd begin to spread out, and then the refraction would narrow them in. And so this is really just also refraction in here. So show that in fact, that's part C, right? Yeah, show that the two diffracted rays in both part A and B are related through the law of refraction. So if I go to prove that, I might do something like this. Part A, I have d sine theta equaling m lambda naught. And in part, and maybe I should call that angle A. And then for number 2, I have d sine of B when it's underwater equals to m lambda naught over n. And then just dividing these two equations, I would have sine of A over the sine of B. And then the m's cancel off, the lambda naught cancels off, and you get n. If you rewrite it without a fraction, this would be sine theta A equals n sine theta B. And I guess I'd say that's the proof, because Snell's law, or the law of refraction, looks like this. N1 sine theta 1 is equal to N2 sine theta 2. And for this particular problem, the part A was in the air, so N is 1. And so theta 1 would be A. And then index number 2 is just what we call just N for that water. And angle number 2 is B. So this is really this applied to where N1 is the air and N2 is the water, and 1 is part A and 2 is part B. So I don't know how exactly they want you to prove it. Let's see what the author does. Let me just check. So B got 19 degrees. Okay, good. And then combining these two equations. Yeah, he just did exactly what I did. Nice.
Awesome. Thank you so much.
Good. That was a fun one. All right, so let's switch back over to the Zoom. And now that we did 49, Daniel Yuskin, you have any? Oh, I bet I do. I totally forgot about that. I should have sent that out this week. Let me take a moment and tell you which ones I do have. Let's see, where would I find that?
It's nice having those, because then we know we have a video solution, and if we need to ask a question on something else that there's not a video solution.
Right. Okay, let me go to my Google Drive here. Give me a second. I remember I didn't set this up very well last year. That was just, we were like just thrown into the pandemic. But I thought I made a folder that was called, oh, I know, I moved it into my teaching, all my teaching stuff, okay, after the fact. And here it is, online help question. Chapter 38. Oh, okay. I only have one. It looks like number 62. So not not all that complete. I wonder why it was only 38, or did I not? Maybe I should scan my YouTube channel. Maybe I didn't write them all down.
Well, one is better than nothing.
Okay, well, good. I'll put it in the chat there too. There it is. If anybody wants to click on that. But yeah, so 62. I should make a note to myself. Number 62 from last year. I'll send that out sometime later today. But now I have a vague recollection of last year. We went on the pandemic hit right at the end of 36. So I think I just did one or two from 36. And then I had quite a few from 37. And then for some reason in 38, yeah, I just remember there weren't a whole lot of questions from 38. Or, oh, I do remember they were. And actually, maybe that does match, because I've answered this week a number of 38, but I think I only made one. Did I make any from 38? Yeah, I might not have. But so most of the questions I've got were questions that weren't really about doing the whole thing. They weren't really about making a whole video. They were just things like, well, why did it come out to be negative and not positive? Or, ones that I just could respond real quickly and I think answer completely with an email. Huh. Well, anyways, so thank you. But that's all I got. I'll move on and we'll keep making more here. Let's go to, how about chapter 38, number 41 from Johnny. Okay. So 38, number 41. Time is 10:34. Okay, so that's the solution page. Where's the question? Okay, all right. So, okay, so 41 is just right before that. And it says what? Make this a little bigger. I can read it. All right. It says, an unpolarized beam of light is incidented on a stack of ideal polarizing filters. Okay, the axis of the first filter is perpendicular to the axis of the last. Okay, so I guess we have crossed ones, but there's a whole stack. So we don't know how many are in this stack yet. Okay, perpendicular. Find the fraction of the transmitted beam's intensity is reduced. Oh, in 3 different cases. So we have 3 filters are in this stack. Okay, so each of them are at 45 degrees. Okay, 4 filters in this stack. 90 divided by 3 would be 30. Yeah, so they'd be 30 degrees apart. Oh, and then 7 filters. So let's see, 90 divided by, is that right? 90 divided by 6 would go in 1 and 5. So they'd be 15 degrees apart. They were even. And that's what it says, 15 degrees relative to the preceding one. All right. All right, so I'll start with A. And the important thing that I should say here as maybe a review is we have this equation that says, all right, if you have a certain intensity and you put it through one of these polarizers, it's the electric field. It's a vector component. And so I guess we really, to understand this, need to go perhaps all the way back to, even when we did vectors for the first time, where we would have to look at the component. So when we did projectile motion in physics 121, and you had kind of this baseball and you throw it at some angle, one of the things you need to know is what is its speed in the x direction. And the other thing you need to know is what is its speed in the y direction. So you need its component. And that's what these filters do. That's why they're called filter. And they're polarizing filters, because they would only let the part of the electric field in a particular direction. So if you already had it in a particular direction, then it would only let a component of it. And since the intensity is the square of that, you would have to then take and square it. And so that's how you get the cosine squared. Well, what I wanted to emphasize before I got started was that would be true only if the light was already polarized, because sometimes you have light that's not polarized. And what that means is the light hitting the filter is in a random direction. Again, meaning sometimes the light at one split second is hitting it at an angle of, say 10 degrees. Another time it's hitting it at 20 degrees. Another time at 90 degrees. Another time at 0 degrees. Anyways, if you add up a bunch of random angles, you get half. You get 45. And cosine of 45 squared is 1/2. So one of the things to always ask yourself when you're starting one of these problems is the light coming in, is it unpolarized or is it polarized? Keep in mind that, of course, once it goes through your first polarizing filter, then it is polarized. So there's never a question after the first filter if it's polarized. It's yes, it's polarized. It just went through a polarizing filter. But the original light may be unpolarized. And if it's unpolarized, then you just say, well, the intensity is equal to 1/2. As I said, it would be over a period of even really just a fraction of a second, the light would be at all these random angles, 3 degrees, 8 degrees, 45 degrees, 79 degrees, and just jump back and forth. And so that's why we call it unpolarized, because there's no set pattern to it. It's made up of a whole combination of stuff. So we just take the average of that over a split time. And so that's what I'm going to do first here. So I would say then that my first bit is to say I have unpolarized light. When it hits the first filter, it's going to be reduced to 1/2. Okay. Then I have polarized light, and it's going to hit the next filter. So the second filter is going to take that intensity and multiply it by cosine squared of whatever the angle is between the first and the second. And for part A, with 3 filters, they say that you have a 45-degree angle between the first and the second. Okay. So that would be the intensity after the second filter. And then the third filter is angled from the second by another 45 degrees. So there's going to be another cosine squared of 45 degrees. And so this would be the total intensity. Like I'll say it again, cut in half because of the unpolarized one. Cut by 45 degrees because of the angle between the second and the third, and then cut by another 45 degrees because of the angle between the third and the second. Now, I suppose I could grab my calculator here, but fortunately, cosine of 45 is that easy one. That's root 2 over 2. And then when you square that, you get a half. So this would be I naught over 2 because of the first filter. This would be a 1/2 because of the second filter. And this would be 1/2 because of the third filter. And so ultimately, the intensity is 1/8 of what it started.
Just a quick question. If it's polarized more than once, or like we can just keep adding on to that, right? So if there were two more steps onto that, we would go ahead and add on 2 more cosines of whatever angle by.
Yeah, yeah.
Okay, cool. Thank you.
Yeah, exactly. And that's what we're about to do. Look at B. B says we have 4 filters. So I would say the intensity is, and so after the first filter, it's cut in half. That's that unpolarized step. Now, after that first filter, it is polarized. And so I would have a cosine squared of the angle between the second one and the first one, because it's how the second one is aligned compared to the polarization, and the polarization was determined by the first one. So maybe I should have said it that way, that the angle is actually the angle between the polarizing filter and the light polarization. But in this case, the light is polarized based upon the axis of the first one. So it really becomes the angle between the first and the second, which in this case is 30 degrees. Now, as we approach the third filter is tilted 30 degrees from the second one. And the second one is the direction that the light would now be polarized because it went through the second filter. So that's why I do another cosine squared of 30 degrees. And now we approach the last filter, which is 30 degrees compared to filter 3. So we've got this mess. Cosine of 30, was that root 3 over 2? Well, I won't even try to remember. I'm just going to get my calculator. Although I think I am in radians. So I will switch over to degrees mode here and go cosine of 30. Yeah, 0.866. Shouldn't that be?
You're right. It's root 3 over 2.
Ah, thank you. Oh, I won't bother to mess with that. Okay, good. All right, so that's cosine of 30. Now, if you look at this, if you don't mind, I'm just going to put these all together. That would be raised to a power of 6. So I'm just going to take my last answer and raise it to a power of 6. And then divide all that by that 2 over there. And I am at 0.211 times the original intensity. And by the way, let me just come back here to A so I can kind of compare, because 1/8 is 0.125. And I think one of the things I always find interesting, and as I'm looking ahead in this problem, they're going to ask about it in part D, is notice that you actually get more light coming through a stack of 4 filters than a stack of 3 filters. And I just realized I didn't really quite answer the question correctly. The question actually says, find the fraction by which the transmitted beam is reduced. And I found how much is left over. All right, so it's this one is reduced by 7/8. So this is reduced by 0.875. So 87% is reduced. I guess I should do the same thing here. 1 minus 0.211. And so here we lost 78.9%. But hopefully my discussion, what I got started on, was interesting here, that actually more gets transmitted through in part B than in part A. Or put another way, the reducing factor in B is smaller than the reducing factor in A. And so we actually get more light through 4 filters in B than we did in A. And there's probably more I should say about that, but I think that is going to show up in C and in D here. So maybe I'll just keep going here with C. C says, look what happens if you have 7 filters. Okay, so let's go through 7 filters. So again, the first filter, because it's unpolarized, cuts out half. So there's the first one. Then the second one is rotated just barely compared to the first, just 15 degrees. So we only have to multiply it by cosine of 15 degrees to get the intensity after the second one. And then cosine squared of 15 after the third. And cosine squared of 15 after the fourth. Cosine squared of 15 after the 1, 2, 3, 4, 5. And after 6. And then finally, one more after 7. And you're probably beginning to see the pattern here. This, of course, was cosine to the 6th because it's squared, and then we had 3 filters. This would be 6 filters, 1, 2, 3, 4, 5, 6. And so it'd be cosine to the 12th. So if I go cosine of 15 degrees and then raise it to a power of 12, I get this crazy number, 0.659. And from the first filter, divide by 2, it lets through 0.330. Is roughly a third. So after going through all 7 of these filters, 1/3 of the energy comes through, which again, the real question is how much gets blocked or reduced. So 0.670 is the reducing factor. But again, let me point out the same thing, that even though there's a lot more filters here, 7 of them, we didn't block out nearly as much as we blocked out when we just had 3. And that's kind of what then I think part D is going to get into, because that's always a little surprising. But I think it's more because of the way you say it than anything else, because you're saying you have 7 filters. And it really doesn't matter how many filters you have. It matters of how much each filter blocks. And since it blocks a component of it, if you have a bunch of filters, like these 7 filters, their angle between them is really small. So even though we have a lot of those filters, we're blocking very little light each time. And so, like I said, I think when you first hear it, it kind of throws you off, and you go, wow, you have 7 filters, and then 3. How did 3 block more than 7? Well, again, because how much they block is related to their angle. So it's not really about how many filters you have. It's about how much is getting blocked by each filter. So I guess technically it's a combination of both. It's a combination of how many filters do you have and how much is getting blocked by those. So with that in mind, it shouldn't bother you that even though we have 7 filters, we get more light through. Because yes, we have more filters, but each filter is so closely aligned with the other one, it's really blocking very little. So it just doesn't have that big of a blockage effect. And then that's what D is, I guess, saying. I just said it in words. Comment when you compare your answers to A and then B and then C. So that's, again, I guess I'd say it this way. It's really not just how many filters. It's a combination of how many filters and how much gets blocked by each filter. But there is something that's just kind of interesting because the first and the last one are at 90 degrees to each other. So if you only had those two, nothing would get through. And every time you introduce more and more filters in there, it actually goes less and less. And that just sounds funny. More and more filters you introduce, the less and less it blocks the light. You're like, wait, aren't you putting in more blocks? Aren't you putting in more filters? Yeah, but what you're really doing is creating an effect that you are essentially just letting the light come in and blocking a small percentage of it.
What would an example be of like a continuous filter throughout like an angle change? Would that just be like cable, fiber optic, or like
no,
like if you wanted to...
Usually a fiber optic doesn't try to have a filter, but there is such things that do this. They're called quarter wave plates. And basically I guess I would say every layer of molecules is a filter. And surprisingly, these can be really small. I mean, even you take something that's 10 microns thick, there are so many layers of atoms by that time that what ends up happening is the light, when it comes in, is already, say it's already polarized. I know the problem we just did had unpolarized. But these quarter wave plates are really nice because remember, the last one is 90 degrees. So it's going to come out polarized perpendicular to that. So you don't lose any of the energy and the polarization changes. And that's where they're useful. They essentially rotated it. In fact, now that I mentioned, there was a problem on the ones that got chopped off on the quarter wave plate. And if any of you are struggling with time and just to learn it, there's a couple in here of these problems that are neat problems, but you probably heard me say in the lecture, we're just out of time. And the one that has the quarter wave plate, I'll look it up. I was reading it this morning. Here it is. See, it's a really neat problem, but it's number 60. Looks like this is number 63, and it kind of explains how a quarter wave plate works. And again, we kind of ran out of time, and it's kind of like all the topics we did. We started with simple stuff. This is only an introduction to optics, and we can only go so far. And we're starting to get some really neat stuff, but it's time just to say, all right, that's good enough for now. You'll be ready for an optics class. Now an optics class, unlike a thermodynamics, is a little more discipline specific. So very few of you will go on to take an advanced optics. Unlike thermodynamics, all of you will probably have to take an advanced thermodynamics. It's just so universal to all the fields. But optics is very specific to what they call photonics engineering and optical engineering. So That one won't be a big one. And there was another one I should say we didn't get to. It was a Brewster's angle. Yeah, I believe it's 54 here. I'll say the same thing. A neat little Brewster. This is a double Brewster's one. But Polarizing Light by Brewster's. We only had enough time to talk about the polarization from the filters. So we didn't do any of the scattering polarization. We didn't do any of the Brewster one. Yet they're here on the assignment. So if you didn't want to do 54, I get it. Or 63, very acceptable.
I think you took both of those off the syllabus because I don't see either 54 or 63 on the syllabus homework set.
Oh, good.
Also, number 36 is a Brewster's problem. You took them all off the syllabus.
Oh, good. I did. Okay.
I didn't realize that until I already did number 36 and I was confused. It's like, wait a minute, what is happening? 36.
Oh, I'm sorry, what?
It was number 36.
36? The angle of incident light beam is reflective of surface.
The solution shows Brewster's.
Oh, completely polarized. Yeah, it is. Okay. Yeah. Okay. How did you know to do 36? Maybe you did the same thing I did. I just started looking at the solutions.
That's what I did. I read the problem like, I don't know, 7 times and was thoroughly confused each time I read it. So I kind of just peeked at the solutions and realized, oh. Okay.
Good. Okay, so I'm glad I took it off the syllabus because I know that originally, long time ago, when I, sat down to teach this class, I think for the first time, and I looked at these problems, I had thoughts and dreams that, okay, I'm going to do Brewster's angles and I'm going to do these advanced stuff. And I think I assigned it, and that's how they got on there, my list. And then I think reality sat in and I go, okay, well, we're just going to have to stop at Brewster's angle. And then, anyways, I'm glad I took them off the syllabus, but I already had made the solution page by that point. And so they're on that solution page. I think that's the history of it. Okay. Good. All right. Well, with that in mind, I should jump over. I think you guys probably have a lot of questions today here. So let's see. So that was number 41. That was from Johnny. Hunter. Good question, Danny. Okay. Then there's me here. Okay. What is the conversion? Oh, Daniel, I'll mention the conversion here. I always think of it this way. That
someone already answered that a little later. So. Oh,
there you go. Yeah, half circle. So it's 180 to pi. So just think of a half circle or a full circle. I was going to just do a full circle, 360 over 2 pi. Of course, then that does reduce to 180 over pi. Yep. And then thanks. All right, good. So then we'll get all the way down to the bottom of that chat there. Hunter, okay. So number or chapter 37. All right, we'll go back a chapter here. Number 59. So chapter 37, number 59 at an even 11 o'clock. Okay, so scrolling up to chapter 37. Yes, it is. And then finding number 59. Oh, Newton's rings. Yes. Good. Here's Newton's rings are always a little challenging mathematically, but it says in a Newton's ring experiment, a plano convex glass of index 1.52 lens having a diameter of 10 centimeters is placed on a flat plate of glass as shown. So here will be my flat glass. And the lens has some curvature and then flat. And I exaggerated in the curvature. I mean, usually these curvatures are just small and there's just a small thickness here, but I wanted to kind of give myself some room to draw in there. And the key here is to realize that light coming down, although will bounce off this top surface, that is really far away compared to the reflection off of this surface and the reflection off of this surface. And I guess technically it would then reflect off this bottom piece. But because my picture is drawn excessively large with a gap here, it almost looks like, you know, I've got these 4 different layers. And what I wanted to start off is realizing where is the thin film? You know, where is the interference of the thin film? And keep in mind, we use that phrase thin film because this is only going to work if they are close together. And so they only work when they're thin. That's why, I'll grab a different color here, but I'm going to scratch this one off because this one is so far removed from that one because, you know, the thickness probably literally is 3 or 4 millimeters from here to here. And that's just too far away for these 2 beams to come back up and be next to each other close enough to interfere. So you only notice this when it's thin. And so I want to emphasize that because sometimes in our drawing, and this is a good example of that, you're looking at this drawing going, well, wait a minute, do I have the interference between this, well, I'll call it first and second reflection, second and third, third and fourth? And so let me just take a moment to point out that looking at these 4 reflections, it's the second and third one that are close together. This is where some interference is going to take place. So that's where I'm going to focus my attention. So I'm going to only call them, and I'm going to rename them 1 and 2. All right, so this will be, these are the 2 that are interfering with each other. And of course, that's important to know because the thin film goes right, you know, in here, and this is what the material is. So the fact that they gave me an index of 1.52 for the lens is useful, but it is not where the extra light travels. And that is kind of important. Usually it's just air because you just, you know, do this on the lab bench. You put down a piece of glass and you put the lens on top of it and everything out here is air. And so most likely this is air. Of course, you could also do it inside a bath of water. So thin film could be made out of water or some other material, but unless they say differently, I'm going to assume it's air. I'm just stacking a bunch of lenses here, or one lens on top of a flat piece of glass. Okay, so it says when 650 nanometers of light is incident normally, 55 bright rings are observed, with the last one precisely at the edge of the lens. Okay, so now they're going to be focusing attention on bright. Now, let me just kind of review what I like to think about in terms of these thin films. The first thing I do is I think to myself about reflection. I go, okay, if I was standing up here, it looks kind of like I'm skydiving up there, but if I was standing here, I would see the reflected light. And so if we called T the thickness of the film, and of course now you can see this is going to be a little more challenging problem. The thickness varies as we move along here. Okay, but let's just say at some point it has a thickness T. This second beam, which goes down and back, travels an extra distance of 2t. And so I like to say if 2t is an integer number of wavelengths in the film, so I'll divide by n, the index of the film. And like I said, for this one, I'm going to assume it's air unless they tell me something a little different later on. But 2t equals an integer number of wavelengths. If that is true, and if that's the only thing going on, there's nothing additional going on, I would get a maximum on reflection. Which would also mean that when 2t equals m plus a half, I would get a minimum on reflection if nothing else is going on. Now, the reason I keep saying nothing else is going on, because we have to consider another effect, and that is what we call the phase shift. When something hits and reflects off, it could either be at its phase or inverted. Now, inverted is taking a crest. So if I point my finger up to represent, up, then the crest now becomes a trough. I suppose another way of thinking of it is to say it's the equivalent of an added half wavelength. And the reason that's important here is because when we said 2t is an integer number of wavelengths, we were saying that the crests were lining up. That's why we said they were a maximum. But see, if one of them went under a phase shift and the other one didn't, they would not be two crests lining up. There'd be a crest and a trough. Now, if they both underwent a phase shift, well, that's the same thing, really. So what I need to do is ask myself, are there any phase shifts here? Because if there's no phase shifts, then I'm done. These equations are valid. And for that matter, if there's two phase shifts, these equations are still valid. So if they each undergo a phase shift, because remember, it's a difference between them. So if they both undergo a phase shift, the thing that I have to really watch for in this is, does one of them undergo a phase shift and the other not? Because then what I would have thought would have been constructive interference now becomes destructive. And what I thought was destructive now becomes constructive. That's the one I got to watch for. All right, so the last part of this thin film thinking is to say, is there a phase shift? And there is when you reflect on something with a higher index. So this first beam is actually in the glass, which has an index of 1.52, and then it's hitting whatever this material is made of. And they don't say, except I'm pretty sure they're directly implying that as a standard experiment, you're doing it in the air. You just put down the piece of glass and the lens on top. And of course, you would have air all around you. So I'm going to say that I have air, and the index of the air is very close to 1. And so this first beam is going from a high index into a low index. So it's bouncing off something that's low, and it'd be no phase shift there. But the second one is then hitting this glass, which has an index of 5.2 from the air. And I like to put little circles around them to remind me, that one has a phase shift. So I would say one undergoes a phase shift and one does not. Therefore, this equation that was giving me constructive interference is now destructive. And this one here, which was giving me destructive, now gives me constructive. That's for reflected light. By the way, once I do that, I also like to just put what would be the condition of transmitted light. And if the light is doing one effect when it's reflected, it's the opposite for the transmitted light. So part of any question with a thin film is to ask, are you looking at the light that is being reflected? So I always derive the equation first for reflected. Even if the problem later goes on to talk about somebody standing over here, in this case, they'd have to be under the lab table looking through the glass. And so that's not what's happening in this problem. But these are the four equations that would be of interest for any thin film. And that would be either the constructive or destructive of reflected light, or the constructive, destructive interference for the transmitted light. And so what are we doing? And again, the way they say it, and they ask you to go look at that figure, we can just say, look, we're not even talking about the transmitted light in this problem. So for this problem, I didn't even need to write that down, but that was just to maybe help you out, because there are some problems where you're looking at the transmitted light. So I'll say it again. I always just start here with 2t equals integer number of wavelength. That gives me maximum reflection. I look at the phases. If one has a phase change and the other doesn't, it switches to minimum. Otherwise, it stays a maximum. And once you know one of them, then you know all four of them. So I usually then just write down all four and then say, okay, what do I want for this problem? So I know I don't want the transmitted light for this problem. But do I want minimums or maximum? Let me come back here. And I thought it said bright somewhere. Yeah, it says 55 bright rings. So the equation that is relevant for this problem is right here. The bright reflection. That's, of these four, I can cross out these other three. Our attention for this problem is on reflected light and bright. That's the equation. And I wish I could always tell you that it's m plus a half for bright, but it's not. It depends on the scenario, right? So you got to think through that scenario. So that's why the physics is really a key step in these thin film ones. All right, well, so I hope I didn't spend too much time kind of lecturing on it, but I got to decide which equation is relevant for that problem. And so I decided that 2t equaling m plus a half over the wavelength divided by the index, which I'm going to call 1 right now. And I'll say it again, I'm calling it 1 because the interference is in this little gap, the air gap, not the glass. That's the relevant equation for this problem. Okay. Now, they also say that you can see 55 bright rings. So let's take this equation and talk about it. See, because if you were to start this, you would say, well, there are an infinite number of integers going with an infinite number of thicknesses. See, and what that means is for m equals, say, 0, there would be a corresponding thickness where you would get this maximum. And so maybe somewhere right in here would be the corresponding thickness that fits with an m equals to 0. And so somebody looking here would say, oh yeah, that's bright. But then a little bit further over, which would correspond to a solution of m equal 1, would be a bigger thickness. And so that thickness would also give you constructive interference. And so you're looking at this, there are numerous different thicknesses that give you constructive interference. That's why there's so many bright rings. There's 55 of them. And so this sequence would go from 0 out to, and I guess the last one would be 54. Because when m is equal to 54, that would correspond to a certain thickness where, again, you would get a bright. And so all of these different marks I'm trying to make on here are spots that this equation is valid. They're valid for a certain thickness and a certain integer. And so the smallest thickness goes when the smallest integer. So the smallest thickness would be here, and it would be bright to your eyes. The next integer, m equal 1, would be a little bit thickness, and that would be a bright spot. And since it would be all the way around the ring or all the way around the lens, it would look like a ring to you. So that's why you would call it a Newton's ring. I'm just drawing a cross section. So the bottom line here is I can find the thickness of the last ring. So the last ring would be way out here on the edge, because that would correspond to m equaling 54. And so our wavelength is 650 nanometers. And so if I grab a calculator now, I can then say, okay, what is that thickness? So 54.5 times 650 times 10 to the minus 9 divided by 2. And we're looking at 1.77 times 10 to the minus 5. And it looks like I did it in meters. So this thickness, the last one of the curvature, is that number. Okay, well, now I have some geometry to do, because A says, what is the radius of curvature? And then of the convex lens, and then B, what is the focal length? That's kind of a review part, but let me start with A. And let me kind of redraw a picture here now that I've drawn so messy on my original picture. So here's the piece of glass. Well, let me make the glass a little wider. I'll make contact right here, and it curves upward, then goes flat across, curves upward. And this has some radius of curvature. I'll put it maybe right about there. So this would be R. And of course, extending out to here would be R. I guess the point should have been a little higher. So forgive my drawing. But here's the real key. Let's call this, and I don't know if this is confusing what I did earlier, because really there's a bunch of different thicknesses that give you the bright one, but I did the last one. So this number T, maybe I should do T sub L for the last T that matched the appropriate thickness to give you a bright one. So this over here is T sub L. And I'm going to take advantage and say, look, that right here then would be R minus T sub L. And this distance right here is the radius of that Newton's ring, which they told us is 10 centimeters. Although I'm going to write it as 0.1 meters. Because this is where the geometry comes in here. I've got Pythagorean's theorem with this triangle. I've got a height here of R minus T sub L. If I square it, and I add it to the 0.1 meters and square it, so that's the sum of the square of the legs, that has to equal the square of the hypotenuse. And now if I FOIL this out here, this is an R squared minus 2RTL plus TL squared plus, and 0.1 squared, 1/10 squared is 1/100th, and then R squared. Fortunately, then the R squareds cancel off. If you move this to the other side, you get TL squared plus 0.01 is equal to 2, and I'll write it as TL over R. And I'm trying to get the R. So this would be TL squared plus 0.01 divided by 2 over TL. And that's then the geometry of how I get the R from the thin film. So obviously the physics part of this chapter is right there, the thin film. How do you get the, that thickness? Then we got to go back to our geometry and our mathematics to do that. But the TL is what I got up here. So that's that number that's still in my calculator. So I'm going to square it and add 0.01. So that's the numerator. Then divide it by 2 and divide it by 1.77 times 10 to the negative 5. Whoa. That's a big number. Although that is a small gap, so it's got to be very little curve. 282.5 meters. Well, at first I was a little surprised how big it is, but maybe not. I mean, it's a pretty small gap, and so that really. Well, I'll tell you what. Let's just look at the answers here. Make sure. What is this? 59. Let's go back to chapter 37. Scroll down to 59. Oh, yeah. See, they only got 70 meters. I like that better. What did I do? Oh, duh. Sorry. Stupid mistake. This is a radius. This should be 0.05. They said the diameter of the Newton's ring is 0.1. So my apologies there. All right. So this is 0.05. And fix that. So this would be 0.05 squared. So let's try this number again here. Okay, so here's the t squared. Let me add 0.05 squared, enter. Let me divide that by A2. And let me divide that by the 1.77 times 10 to the negative 70.6 meters. Okay, I do like that a lot better. So, yeah, sorry about that. That was really dumb, confusing radius with diameter, but seems to be common, easy to do.
Yeah, the geometry is probably the hardest part too. It feels like, at least.
All right. Okay, so once we got the radius, then let's go. I'll go back to the question, but I think the question said, what is the focal length? So here we'll have to go back to the chapter 36, where we had the lens maker equation that said 1 over the focal length is n minus 1 over r1 minus 1 over r2. So there's our geometric optics. And maybe I'll just kind of draw the lens here. One of the things we did learn in 36 is you get the same focal length regardless of which way the light's going. Because you keep that in mind. You may be wondering, do you set up the lens so that it hits the plane first or it hits the convex first? And it doesn't matter. It come out to be the same focal point. So I'll just calculate it this way. All right, so 1 over the focal equals, and so now we need that index of 1.52 and subtract the 1. Then we need 1 over R1. And the definition of R1 is the radius of curvature of the first surface. And this is flat. And so this would be a radius of curvature of infinity. If you'll let me put 1 over infinity. I could just put 1 over big. Either way, 1 over big is just equal to 0. So that's going to go away. Then it's going to hit this curvature that we just calculated, which is the 70.6 meters. However, you might need to remember from the last chapter, our definition of a positive R is where the light goes. And so this radius is on the side the light comes from. So this is actually a negative radius of curvature set up this way. Now, had we done it this way, it would have been a positive radius of curvature, but it also would have shown up at R1 here. So that would have come out positive, and then these two negatives are going to make it positive. So that's why the math would come out to be the same. All right, so I'll just, two negatives make a positive. Won't worry about the negative. The 1 over big will be a 0, so I won't worry about that. And then this would just be 0.52, and I'll divide it by 70.6 and get 1 over f is that thing. I won't even bother to write it down. I'll just hit reciprocal. And so we're looking at a focal length of 135.8 meters. So pretty long focal length, but given the small radius of curvature, that's not a surprise. I'll check the answer. Yeah, it does match. And that also being said, it probably makes sense for Newton, because what he was playing with were these lenses that were used in telescopes. And part of the angular magnification is the focal length between the objective piece and the eyepiece. So anyway, so that's, you want a big, long focal length, when you make a telescope. nice to have a really long focal length for the objective piece, and then a small one for the eyepiece, because the magnification, the angular magnification, is the ratio between those two. So try to make this one big and try to make that one small if you're trying to see something big. And that, because I should be careful. You don't always want to see something big. You know, looking at the moon can be kind of boring if you magnify it too big. All you can see is inside a center of a crater, and it's more exciting to see the whole crater and mountain ranges. So it's easy to over magnify when you look at the moon. That's why actually the moon is really nice with binoculars. A good pair of binoculars is better looking at the moon than a telescope, unless you want to see an actual mountain range. But if you want to see the whole moon, telescope, you just lose the whole moon and lose the beauty of the shadows and the mountains. And yeah, so
Awesome. Thank you so much.
yeah. Anyway, yeah, I'm just chit chatting again. Okay, so I just can't stop talking.
No, you're good.
All right. Well, we'll see. Is there anything else in the chat? Or are we here near break time? Ryan, number 9 on the practice problem. All righty. Ryan, are you in here?
He's not sitting at his desk, it looks like.
Okay. Did I?
When do we normally take break? Is it noon, 11:30 or noon? I forget. It's been a while.
Oh, yeah, I got to look to my time. It's 11:30. So, well, I'll tell you, why don't I write it down, and I'll just do that first thing we come back. Be a good time for a break, and then he's not here, or he's coming back. Here he is now. Hey, Ryan, we just talking about you. We're thinking that why don't we take our break, and are you going to be able to be here at 12:30?
Yeah, I think so.
Well, if you can, we'll do it at 12:30. Otherwise, if you can't, let me know. I'll do it now.
Yeah, 12:30 works.
Okay. All right. So I'm gonna write that down. Practice problem. That's from the test, right? Number.
Yeah, the last one on the test.
From test. Yeah. Okay. And we'll do that first thing at 12:30.
All right.
And,
Sounds good.
all right. All right, guys, I will take a little break, maybe get myself something to eat and take a walk, and then I'll see you 12:30. How's that?
Thank you.
How about that? Thank you.